Hello everybody. In the previous video, we saw the various applications of the signal processing, the various tools, the various aspects in which signal processing is extensively used. Now we will go slightly deep into some of the tools and applications of the signal processing. Okay, first one is Kalman filtering, next is sensor fusion, and next is radar signal analysis in ADAS. Now what is Kalman filtering? Kalman filtering is a recursive algorithm that estimates the state of dynamic system from noisy measurements. This sentence you please clearly understand, that estimates the state of dynamic system from noisy measurements. Okay, it gives a very appropriate or accurate estimate of the dynamic system from noisy measurements. It works in the two steps. First is predicts. It estimates the next state based on the model, or estimation means extrapolation, and when it comes to correction, it updates the estimate using new sensor data. Okay, it is optimum, minimizes mean squared error for linear systems with Gaussian noise. When it comes to types of Kalman filters in ADAS, the various types of Kalman filters are linear Kalman filter, and it is used in basic state estimation, and it is used in tracking a vehicle's position with radar. In the ADAS context, the linear Kalman filter is used in tracking vehicle's position with radar. And when it comes to extended Kalman filter, the use case is non-linear systems like vehicle motion, which is usually non-linear. Here it fuses LiDAR with camera data. Third, unscented Kalman filter, which is acronymed as UKF. And UKF comes to highly non-linear systems. And one use case of ADAS is predicting pedestrian movement. Pedestrian motion is an extremely non-linear, non-predictable system or aspect, and predicting that non-predictable system comes under the purview of unscented Kalman filter. Next comes the particle filter. Particle filter is non-Gaussian noise, multimodal distributions, handling sensor ambiguity in complex environments. Okay. Now, how Kalman filtering works in ADAS? When it comes to Kalman filtering, first is the state prediction, where a car will be 0.1 second based on velocity. Okay, understand this sentence carefully, where the car is going to be in the next 0.1 second based on the velocity. Next comes to measurement update. Radar detects the car's position. Fusion combines prediction and measurement for best estimate. Alright, so prediction and measurement are both important, and when both prediction and measurement is fused, it gives the best estimate. For example, adaptive cruise control uses Kalman filter to track the leading vehicles speed and distance. And when it comes to lane keeping asset, it predicts the vehicle's trajectory and correct steering. So below two illustrations clearly show this is adaptive cruise control and this is lane keeping assist. Okay, in both these ADAS functionalities, Kalman filtering is extremely of paramount importance. Now, when it comes to sensor fusion in ADAS, why is sensor fusion needed? Because no single sensor is perfect. Okay, this I clearly explained in the session about sensor fusion, but in this context, please understand, cameras fail in the fog, radar has low resolution, and when you combine or integrate the signals from various sensors, it improves the reliability, reduces false alarms. Okay, now common sensor fusion techniques. Example, radar plus camera fusion. Radar detects an object's distance and speed but poor angular resolution. Camera classifies the object but struggles in low light. Kalman filter fuses both to get accurate position plus identity. Now, how does it work? Kalman filter based fusion combines predictions plus measurements and ADAS application is radar plus camera tracking. Okay, and radar plus camera tracking is extensively used for adaptive cruise control or automatic emergency braking. Now, when it comes to deep learning fusion, neural networks process raw data or pre-processed data. Tesla's Hydronet is a very major ADAS application which uses the deep learning method. And next comes the Bayesian occupancy grids. This is useful to guess the probabilistic mapping of the obstacles. Okay, to guess or to estimate the further mapping of the obstacles, Bayesian occupancy grid is used. And when it comes to ADAS application, it is autonomous parking or self parking, where the vehicle computer itself handles the driving, the accelerator and also the braking. Now, when it comes to decentralized fusion, example federated Kalman filter, here each sensor processes data locally. Now, the main application is V2X systems. Whenever you see a sensor processing data locally or within the sensor itself, then understand that ADAS application is nothing but V2X systems. All right. Now, let's see the signal processing importance in elaborated manner in radar signal analysis in ADAS. Radar transmit radius frequencies waves typically 24 GHz or 77 GHz. Next comes measures reflected signals to compute. Okay, this measures the reflected signals to compute, that is, and what does it measure? It measures the distance, it measures the speed, it measures the direction. And how does it measure the distance? Based on the time of flight. And how does it measure the speed? Based on the Doppler effect. And how does it measure the direction? Beam forming or MIMO radar. All right. Now, when it comes to key radar signaling processes steps, the pulse compression, first step is pulse compression. And what is the technique used? Matched filtering and FFT. Okay, Fourier frequency and timing. And what is the purpose? Improves distance resolution. Now, when it comes to Doppler processing, again it is FFT based velocity estimation, detects moving objects. And when it comes to CFAR, constant false alarm rate detection, the technique used is adaptive thresholding. And the purpose is it reduces the false alarms, for example, rain clutter. Now, next comes the angle estimation. Now, as I already said, when it comes to angle estimation, radar is slightly poor, but still there are some techniques like music, e-split algorithms which determines the object direction for lane changes. Let me reiterate, when it comes to angle estimation, radar is not exactly very accurate. It can only estimate to a decent extent. Now, what are all the, for example, automatic in emergency braking, radar detects an obstacle and estimates the distance and speed. And Kalman predicts if a collision is imminent. And fusion with camera confirms it is a real vehicle and not a false alarm. And then ADAS triggers brakes if the risk is high. Now, in a small example like automatic emergency braking, you could clearly understand the role of Kalman filter and also the role of fusion, which play a pivotal role in understanding the efficacy of this automatic emergency braking. Okay, radar detects, Kalman filter predicts. Next, fusion along with the camera ensures it is not a false alarm, and then ADAS triggers the brakes. It is the final execution or the final actuator. All right. Now, to further continue, what are the various challenges and future trends? The current challenge is radar clutter. Rain, metal bridge cause false detection. So, even if it is raining, radar can give a signal which can be perceived as an obstacle. Okay, even in rain, even if the rain is heavy, the radar may get reflected from the rain droplets, and it may give a message that there is some obstacle. Next comes the sensor misalignment. When it comes to sensor misalignment, in the case of a small accident or a small fender bending also, calibration errors degrade the fusion accuracy. And next comes the real-time constraints. It must process the data in milliseconds. Now this is a very important challenge, or this is the main challenge on which many scientists and engineers are working. Now what are the future improvements? 4D imaging sensors. The future improvement is the 4D imaging sensors which have a higher resolution to get better object separation. Next comes AI enhanced fusion, transformers for better multi-sensor integration. And next is quantum radar. Experimental could eliminate interference. Okay, this quantum radar is a very state of art radar. It is still on the experimental level, it is still in the research level, but the main advantage is it could eliminate the interference. And when it comes to summary, now summary is the various types of the applications. Kalman filter predicts and corrects the object states. Fusion combines radar and camera, lidar for robustness, and radar signal processing. It extracts distance, speed and direction. So these technologies work together to make ADAS accurate, reliable, and what's the last word? I am sure everybody will have guessed. The last word is it makes ADAS more safe. Thank you.